Hello, this is Dr. VC Sontake and I am going to take the course Heat Transfer. Objective of this video lecture is to explain the concept of critical radius or critical thickness of insulation and its significance with regard to the heat transfer rate. So let us first find out what is the effect of providing insulation layer on the heat transfer rate through the body over which this insulation is provided. In order to understand the effect of providing insulation layer on the heat transfer rate, let us first discuss some basic things about the insulation. When we provide insulation over the surface through which heat transfer is taking place, by providing insulation, we generally mean that it will reduce heat transfer rate through that body. However, this is not the case always. In some cases, it is quite possible the insulation from its very nature are used to reduce or to prevent heat transfer rate or heat loss rate from the body over which they are provided. The increase or decrease of heat transfer rate depends upon the shape of the body, whether that body is of shape of plain wall or slab, cylinder, sphere, or any other shape through which the heat transfer phenomena is taking place. The heat transfer rate or the increase or decrease of heat transfer rate by providing insulation will also depend upon the fact that whether the total thermal resistance is combination of only conductive thermal resistance or of conductive and convective thermal resistances. In the discussion of composite wall, composite cylinder and composite sphere, we have discussed the total thermal resistance of the body or the system, thermal system through which heat is taking place. The total thermal resistance can be summation of either the purely conductive thermal resistance or can be summation of conductive and convective thermal resistance if the system is separating hot and cold fluid. So in order to understand the concept of critical radius or critical thickness of insulation, let us first explore the effect of providing insulation layer on the plain slab or wall separating hot and cold fluid. In this case, the shape of the body is in the form of plain wall or plain slab. So let us first consider the case 1. The body is in the form of plain wall having thermal conductivity K and its thickness in the direction of heat transfer is capital L. The plain wall is separating hot fluid film on the left hand side having its temperature Ti and convective heat transfer coefficient Hi, and a cold fluid film on the right hand side having its temperature and convective heat transfer coefficient To and Ho respectively. By virtue of the temperature difference between hot and cold fluid Ti and To, heat transfer will take place from hot fluid to the cold fluid and through the plain wall, and let's say the rate of heat transfer is Q1. By virtue of the heat transfer rate through these three mediums, each medium will offer thermal resistance to the path of the heat transfer rate Q1. The hot fluid film will offer convective thermal resistance, the plain wall will offer conductive thermal resistance and the cold fluid film will once again offer convective thermal resistance. As a result of this, temperature drop will take place from Ti to T1 in the hot fluid film, from T1 to T2 in the plain wall, and from T2 to TO in the cold fluid film. The thermal circuit for this arrangement can be shown where the convective thermal resistance RTI will be offered by the hot fluid film between the temperature Ti and T1. Conductive thermal resistance RT1 will be offered by the plain wall between temperatures T1 and T2, and convective thermal resistance RTO will be offered by cold fluid film between the temperatures T2 and TO. And the total rate of heat transfer Q1 for the case 1 in terms of hot fluid and cold fluid temperatures Ti and TO can be given by the formula Ti minus TO over 1 upon HIA plus L by Ka plus 1 over HIA, where A is the area normal to heat transfer and currently it is not visible from this direction. So here this will be convective thermal resistance, this will be conductive thermal resistance, and this will be once again convective thermal resistance. Now let us consider the case 2. Here the same arrangement is considered as in case 1, with the difference that one insulation layer shown in the green color with the thermal conductivity K1 and thickness L1 in the direction of heat transfer is provided between plain wall and cold fluid. Once again, by virtue of the temperature difference, heat transfer will take place, let's say at the rate Q2 from hot fluid film to the plain wall to the insulation layer and to the cold fluid film at the last. The thermal circuit for this arrangement is shown in figure, where RTI is the convective thermal resistance by hot fluid film, RT1 is the conductive thermal resistance between by plain wall, RT2 is the conductive thermal resistance offered by insulation layer, and RTO is the convective thermal resistance offered by cold fluid film. The rate of heat transfer Q2 in terms of temperature difference Ti and TO can be given as Ti minus TO over 1 over HIA plus L by Ka plus L1 over K1A plus 1 over HIA. Now, what is point worth mentioning here is that with the provision of the insulation layer, the extra conductive thermal resistance is added to the denominator, and because of the addition of this conductive thermal resistance by this insulation layer, the heat transfer rate Q2 will decrease as compared to Q1. Once again, let us consider one more case here. Case 3 with the same arrangement as shown in the case 2, with the difference that a second layer of insulation shown in the pink color is provided between insulation layer 1 and cold fluid film. The thermal conductivity of the second layer of insulation is K2 and thickness is L2. Now by virtue of temperature difference, heat transfer will take place from hot fluid film to the plane wall to the insulation layer 1, insulation layer 2, cold fluid film, and finally it will out. Let's say the rate of heat transfer is Q3. By virtue of the heat transfer through the different material of this system, temperature drop will take place in the hot fluid film from Ti to T1, in the plane wall from T1 to T2, in the insulation layer from T2 to T3, and in insulation layer 2 from T3 to T4, and finally temperature drop will take place from T4 to TO in the cold fluid film. The thermal circuit for this arrangement is shown in figure. RTI is the convective thermal resistance by hot fluid film between temperature Ti and T1. RT1 is the conductive thermal resistance by plane wall between temperature T1 T2. RT2 is the conductive thermal resistance by insulation layer 1 between temperature T2 T3. RT3 is the conductive thermal resistance by insulation layer 2 between the temperatures T3 and T4. And finally, the RTO is the convective thermal resistance offered by cold fluid film between temperatures T4 and TO. And equation for heat transfer rate Q3 will be Ti minus TO 1 over HIA plus L by Ka plus L1 by K1A plus L2 by K2A plus 1 over HIA. Once again, here point worth mentioning, with the addition of second layer of insulation, an additional conductive thermal resistance is added in the denominator, and because of this, heat transfer rate Q3 in case 3 will be less than heat transfer rate in case 2, which is less than heat transfer rate in case 1. So from this analysis, what I can summarize, in case of plane wall or slab, as the thickness of the insulation increases or more and more number of insulation layers are introduced between hot and cold fluid, the heat transfer rate will decrease. So I can straightaway say that if the geometry is plane wall, by providing insulation or by increasing the thickness of the insulation, heat transfer rate will decreases. So I can summarize the effect of providing insulation on plane slab or wall separating hot and cold fluid. So in case of plane wall, increase of insulation thickness decreases the heat transfer rate linearly. In plane wall, area normal to heat transfer remains constant even when I provide the insulation layer. Hence, increase of insulation thickness increases conductive thermal resistance without affecting the convective thermal resistance. So as the conductive thermal resistance increases, heat transfer rate decreases. Hence, in case of plane wall, more will be the insulation thickness, less will be the heat transfer rate. This is the conclusion I can draw from the analysis. Now let us find out the effect of providing insulation layer on cylindrical or spherical surfaces or geometry separating hot and cold fluid. So let us consider a cylinder shown in the green color. It is provided with insulation layer over it, and this insulation layer will also be of cylindrical shape. Let us say this cylinder is carrying hot fluid inside, having its temperature and convective heat transfer coefficient Ti and Hi respectively. This entire cylinder is exposed to the cold fluid from the outside at a temperature To and convective heat transfer coefficient Ho. Let's say inner radius of this cylinder is capital Ri, outer radius of this cylinder is R1, and outer radius of insulation provided is Ro. Let's say thickness of this cylinder and insulation is capital L. Let's say thermal conductivity of cylinder material is Ki and thermal conductivity of insulation material is Ko. By virtue of the temperature difference between the hot fluid flowing inside the cylinder and cold fluid flowing outside, heat transfer will take place from inside to the outside at the rate, let's say, Q. Here I am assuming the heat transfer is taking place only in radial direction and there is no heat transfer in tangential or axial direction. The thermal circuit for this entire arrangement can be shown as shown. RTI is the convective thermal resistance offered by the hot fluid film between the temperature Ti and T1. RT1 is the conductive thermal resistance offered by the cylinder material between the temperature T1 and T2. RT2 is the conductive thermal resistance offered by the material of insulation between the temperature T2 and T3, and RTO is the convective thermal resistance offered by this cold fluid film to the heat transfer rate Q between the temperature T3 and TO. So these two resistances will be conductive in nature and this will be convective in nature. So the rate of radial heat transfer Q in terms of the temperatures Ti and To can be given as follows: Ti minus To over total thermal resistance, which is summation of RTI plus RT1 plus RT2 plus RTO. The rate of radial heat transfer Q can also be given by Ti minus To. This convective thermal resistance of hot fluid can also be given by this expression 1 over HIAI. Conductive thermal resistance of the cylindrical wall is given by 1 by 2 pi K1L log of R1 over Ri. Conductive thermal resistance of the insulation RT2 is given by 1 over 2 pi K2L log Ro by Ri. And finally, the convective thermal resistance of cold fluid film is given by 1 over HO AO, where AI is the inside surface area of the cylinder and AO is the outside surface area of insulation material. The rate of radial heat transfer is further expanded, Ti minus To. This AI is nothing but inside surface area. So 1 over Hi into 2 pi RIL plus 1 over 2 pi K1L log of R1 to the Ri plus 1 upon 2 pi K2L log of Ro by R1 plus 1 over HO 2 pi ROL. 2 pi RIL is inside surface area, 2 pi ROL is outside surface area. Now in this expression, RT2 is the conductive thermal resistance of insulation layer 1 upon 2 pi K2L log of Rho by R1, and RTO is the convective thermal resistance of insulation layer 1 upon HO 2 pi Rho L. Now, in order to understand the effect of this insulation on the heat transfer rate from cylinder or sphere, we need to understand the effect of these two thermal resistances. Now, in case of cylinder or sphere, when they are separating hot and cold fluid, the total thermal resistance is summation of conductive and convective thermal resistances both, as we have seen in the expression of radial heat transfer for this cylinder. Now, for the cylinder or sphere of fixed inlet and outlet radius, let's say Ri and R1 in this case, and is provided with insulation, with the increase of outer radius Ro, that is also insulation thickness of insulation layer, the conductive thermal resistance of insulation layer given by 1 over 2 pi K2L log of Rho by R1 increases, because as the Rho increases, this term will increase, and in turn the conductive thermal resistance will increase. Whereas the convective thermal resistance of insulation layer RTO given by the expression 1 over HO 2 pi ROL will decrease, because as the RO will increase, denominator will increase, and in turn the RTO will decrease. Thus, for a single wall cylinder or sphere of fixed inner and outer radius Ri and R1 in this case, an increase in outer radius Ro of insulation layer increases the conductive thermal resistances logarithmically, because Rho by R1 is the function of log, and at the same time decreases the thermal resistance at the outer surface, which is also called as convective thermal resistance, linearly. As we can see in figure 1, with the increase of this radius Rho, the convective resistance or surface resistance decreases, whereas conductive thermal resistance or the material resistance increases. And depending upon which one predominates, total thermal resistance first decreases and then increases. So this is the point which is of our interest. What is that point at which total thermal resistance is minimum? Before this it is decreasing, and beyond this it is increasing. That we need to find out. Now, considering the total thermal resistance, which is proportional to the sum of these two resistances, the rate of heat transfer may increase first as insulation is added, that is Ro, to a bare pipe or cylinder or wire or sphere, and after reaching maximum value it starts reducing with the increase in insulation thickness. So as shown in figure 2, let us compare figure 1 and 2. As the total thermal resistance decreases, first heat transfer rate will be increasing. At this point, the total thermal resistance will be minimum, so heat transfer rate will be maximum. Beyond this point, total thermal resistance increases, so total heat transfer rate will increase, because Q is inversely proportional to thermal resistance. So from here you can observe here there is a point, or there is a limiting value of radius of insulation at which the thermal resistance is minimum, so heat transfer rate is maximum. Below this radius of insulation, thermal resistance decreases, so heat transfer rate increases. Beyond this radius of insulation, thermal resistance increases, so heat transfer rate decreases. So this is the critical point, or this is the critical radius of insulation of, okay, at which the heat transfer rate is maximum. Below this, heat transfer rate is increasing, and beyond this, heat transfer rate is decreasing. So from the discussion, from this entire discussion, I can sum up, or I can have one very important conclusion. The thickness of insulation up to which heat flow increases and after which heat flow decreases is termed as critical thickness. And if the body is of shape of cylinders and spheres, this critical thickness is called as critical radius of insulation. From this entire discussion, we have got one very important term called as critical radius. It is the radius of the insulation at which heat transfer rate is maximum, below which heat transfer rate will increase, and beyond which heat transfer rate will decrease. Now, application of the concept of this critical radius or critical thickness of insulation. So the concept of the application, the concept of critical radius of insulation is applied in providing insulation over steam pipe and electrical cables. Let us discuss how the provision of insulation in these two cases are different from the point of view of heat transfer rate enhancement or decrement. Let us first consider the provision of steam pipe insulation. Steam pipe, as shown in figure, it is used to carry the steam from the boilers to the different parts of the power plant or machineries. While this pipe is carrying the heat, the enthalpy or heat energy of the steam must not be lost, because steam is the hot fluid, and if it is exposed directly to the atmosphere, that is air, which is cold, heat transfer will take place from the steam to the cold air, and its enthalpy or heat energy will lost. So it is provided with some insulating material like glass wool, silica wool, ceramic wool. Now question comes, what should be the outer radius of this insulating material? Okay. Just now I have discussed the concept of critical radius of insulation. So in case of the steam pipe, we want heat transfer rate or heat lost from steam to the environment should be as minimum as possible, as 0. And this is the curve we have. So keeping in mind the variation, keeping in mind the nature of variation of the heat transfer with reference to the radius of insulation, what should be this R2? So in this case, we want heat transfer rate to be decreased or minimum. So this outer radius of insulation will be much greater than critical radius of insulation. Now let us consider how far it is different from provision of insulation over electrical cables. Electrical cables are used to carry the electricity, and by virtue of the Joule's effect, heat is generated inside these cables at the rate I square Re, where I is the amount of current the cable is carrying and Re is electrical resistance. Now these electrical cables are also provided with PVC insulations of different layers. At this moment, no need to bother about the insulation class. So when these electrical cables are provided with insulation, PVC insulation, the question comes, what should be the radius of insulation? This insulation over these electrical cables are provided to prevent the users to get electric shock. Okay, if the bare cable is used, the user may get electric shock. The question comes, what should be the outer radius of this PVC insulation? Now, in case of electrical cable, this heat generated due to Joule's effect must be dissipated at the rate at which it is generated. Under such conditions, there will be no accumulation of heat within the cable and it will be remaining at its optimum temperature. So here, the thickness of insulation or the radius of insulation selected should be such that corresponding to that radius of insulation, heat transfer rate should be maximum. And from the nature of variation of this curve, we want our PVC insulation to be in this range. Okay, so in this case, the outer radius of insulation should be less than critical radius of insulation. Here we want minimum heat transfer rate. So critical radius of insulation must be outer radius of insulation must be greater than critical radius of insulation. Here we want maximum heat transfer rate from the insulation. So outer radius of insulation would be less than the critical radius of insulation. There are many more applications of the concept of critical radius of insulation. So learning outcomes. At the end of the lecture, learner will be able to, or after watching this lecture, learner will be able to explain the concept of critical radius or critical thickness of insulation and its thickness and its significance with regard to the heat transfer rate. Thank you for your kind attention and passionate listening. Happy learning.